Okay, so the next talk in the session, Joomy will be talking about verified foreign function interface between Coq or Rock and C. And Joomy will take it away in a moment.
Hi. Okay. All right. I probably should have added Rock to the title, but we're a little too late for that. Hi, I'm Joomy. I'm a researcher at Bloomberg. Today I'm going to talk about a verified foreign function interface between Coq and C. It's a paper based on my PhD work. It is joint work with Kathrin and Appel. In the real world, almost all programs are written in multiple languages and then linked together. Parts written in different languages can be verified separately, but how do we prove that when these parts are combined into one multi-language program, that it still works correctly? Many have studied this problem, and recently the common approach has looked vaguely something like this. We have code in two different languages that we want to link. We define a combination of these two languages, and then we treat these programs as programs in the combined language. This is an idea from Matthews and Findler, and it's often referred to as the multi-language semantics approach. This is brilliant and necessary for the general case, but it's also a clunky way to reason about multi-language programs. It requires extra indirection, duplicated proof efforts, etc. But what if we didn't have to cover the general case? Can we avoid this formula then? We think we can, because languages we choose have a particular overlap, and that overlap goes like this. We have some Coq code and some C code that we want to link together, but also we have a verified compiler from Coq to C. This is the Coq project that has been in the works for the last 10 years or so. And now that we have the C version of our Coq program, we can link that with our C program and reason about the combined program using the verified software toolchain, VST, which includes a program logic for C based on separation logic. So I want this to be takeaway one. Since the source language of our compiler and our language of reasoning coincide, they're both Coq, and the target language of our compiler and our language of foreign functions coincide, they're both C, we can avoid a traditional approach to multi-language semantics. Just to get a better sense of the big picture, we also have a verified garbage collector implementation, thanks to Wang et al. We build our work upon their graph library. And this setup constitutes our project, which we call VeriFFI, which is a verified foreign function interface between Coq and C, where you can call C functions from Coq. Coq program components are proved correct directly in Coq. C program components are locally proved correct using VST, and the connection is made via VST function specs that are generated by our system. So let's dig a little deeper into our setup. Suppose we want to write a program that uses machine integers. So until recently, this wasn't possible in Coq. You would have to use an inductive type for integers in your program. There were hacks you could do with extraction, but those can disregard the hardware guarantees that you got through the proofs that you finished through blood, sweat, and tears, and we don't want that. So here's the setup that we propose. We define an interface, we define an API for unsigned 63-bit integers in the standard way as a module type in Coq, which is like a module signature in ML, and we have an abstract type and some operations defined on an abstract type. We want to write proofs about this interface, so we give a purely functional definition of this interface, and we can reason about client programs of this interface using that functional model. And all of that reasoning is plain conventional Coq. On the other hand, we write foreign functions that satisfy this interface, and we prove that these functions play nicely with the Coq program compiled to C via Coq, and that they play nicely with the functional model. And all that reasoning is a conventional VST proof. And all the required mechanisms in the middle are generated by our system, VeriFFI. So this is takeaway two. VeriFFI allows you to do conventional reasoning in Coq and VST separately and connects those proofs together. So let's start with the operational side. We declare an axiom for the type itself and the operations on it to tell Coq that these don't have a plain Coq implementation. These functions are going to be realized when we compile to C and link with the foreign functions written in C. It's a standard practice in Coq when you want to define foreign functions. We register these references with the Coq compiler and actually provides implementations of these functions. And now we're free to write our own functions that use machine integers, like this dot product function on lists of integers. We can compile this function to C using Coq, and that's enough for the operational part of the foreign function interface. So we're like conceptually at the state of the art for 1995. Okay. Let's talk about the correctness of these functions. How do we know that the C functions we wrote are one, safe, and 2, functionally correct. Our idea is to write and prove VST specs about these C functions that express that. So let's start with the functional correctness. To reason about the functional correctness of the C function, we must write a purely functional model in plain coq of what these C functions actually do. This can be a module that implements the module type that we had before. In this module, we define an integer type to be the inductive natural number type with a bound. We define its operations to respect modular wrapping, just like how machine integers work. If we were to actually run this, that's going to have terrible performance, but that's OK, because it's just for proofs. It's an easier interface to write proofs for. So let's attempt such a proof. We can take the toNat function here as an example. It's supposed to convert a machine integer into a coq natural number. So we want to state as a spec for this implementation of toNat that it does the same thing as our functional model for toNat. And thankfully, VST is a great tool for such proofs. So if you were to write the spec for that by hand, that's what that would look like. There's a lot here. You don't have to follow all the details. Very roughly, what we're saying here is this. Given some runtime info and an input to the functional model, if the C function takes a value that corresponds to the functional model input, then the C function returns a value that corresponds to the functional model output. So there are a lot of details here about heap graphs and isomorphisms and stuff. See our paper for the explanation. And so far, this is just a spec. We then claim that the C function body follows the spec, and we write the proof by hand. So the cool part is, if we have a complete proof of this spec, that means our foreign function is 1, type safe, and 2, correct with respect to the functional model, though we do not have a proof of that type safety. Oh, yeah. So I know this is overwhelming, and thankfully only certain parts of the spec vary from function to function. So maybe we can find a way to account for these variations. So one idea is to keep them in a record. And here's what that looks like. We have a function description, which includes everything we have to know about this function. And most importantly, it has a reified description of the function type. And thanks to this description, we can ensure that the foreign function and the model function in this record actually abide by that type. And in the reified description, we have annotations of each component of the type with a type class instance. So in the function description, we use these instances to hold info about type-specific memory representations. And once we finish the function description, we can then compute a VST spec from that and start writing our proof. So not to sound like an infomercial, but there's even more. We can also generate the function descriptions automatically using a generator that we wrote with Metacoq. So I want to talk a little bit more about reified descriptions, since I believe it's one of our scientific contributions. This contribution comes from our realization that we have a choice about how we generate things. We could choose to take foreign types and functions and generate a scary VST spec directly from that with a colossal metaprogram. Or for parts where we write VST proofs by hand, we would write a long proof that's hard to follow. So we can call that the monolithic generation approach. But that's not ideal. There are a couple of reasons. One of them is that we use Metacoq for code generation, which has a coq plugin for compile-time metaprogramming, like template Haskell. Metacoq's representation of coq terms is low-level by design, because their main goal is to reason about coq's meta theory, so that's understandable. But this means it's a bit more cumbersome to use it for code generation. Another reason is that metaprograms are hard to reason about. It's harder for us to tell if our metaprogram generates the right thing and that it always works. Reasoning from a meta level above can get clunky. And the third reason is that writing proofs this way requires a much deeper understanding of how everything works, which will render our system unusable for most users. So here's what we suggest instead. We come up with an intermediate representation, that is reified descriptions. We can generate these descriptions using compile-time metaprogramming. But for the rest, we don't need compile-time metaprogramming. We can write coq functions that take these descriptions and compute whatever it is that we need. This way, we isolate the metaprogram to the first half of generation, or we can write VST proofs with these abstractions, which makes them easier to write. So now we're ready to see what a reified description is. And as a metaprogramming term, reifying means representing a language construct as an explicit object in that language. So here we're trying to define an inductive typing coq that describes different components of a coq constructor type or a function type. And those components are type parameters, arguments, and return types. We have a constructor for each of these, which gives us the benefits of deep embedding. We can identify what part is what. But also, notice that these two cases take a function as an argument. So thanks to this higher-order abstract syntax-like approach, we get the benefits of shallow embedding. Most importantly, we get to annotate the description with top-class instances, that's what the backtick syntax is in Kork, that are actually indexed by the type of the component. And these annotations have access to the same binder context as the type component. So this allows us to describe even complicated dependent types. So there are other approaches that try to combine deep and shallow embeddings. Their work is more general than ours, which requires complicated mechanisms like the universe pattern. By not being general, once again, we avoid that complexity. Here we're describing a part of Kork within Kork, so we can annotate these components with Kork top-class instances. And that is other takeaway from this talk. By making a describer and a describee the same language, they're both Kork, and using higher-order abstract syntax, we can handle dependent types and annotate each component in a concise and type-safe way. And also, as I said before, we have generators for reified descriptions of function types and constructor types written with Metakork. Well, why did we go through all this trouble? What do reified descriptions actually buy us? The most important aspect is type safety of our specifications. If we have a description of a particular function, like 2 nats, we can recover the original types from that. So here we recompute the type of the 2nat foreign function from its type's description. We can do the same thing for the functional model type as well. And thanks to this, we can build a larger dependent type record, like the function description, that has a type description and also the functions that actually are of that type. The other thing that we use reified descriptions for is rewrites of foreign function calls to functional model calls. Here's the problem. We know dependent type checking involves evaluation. Our foreign functions, on the other hand, do not evaluate. So if we try to prove a lemma like this that has foreign function calls inside, we have a problem, because we cannot unfold these definitions and continue our proofs. This is what happens. Since these functions are axioms on the Kork side, they get stuck. These functions evaluate in a compiled program, because then they're realized by the C implementations, but that's not good enough for compile time evaluation of them in type checking. Well, what do we do? So our solution to this is a rewrite mechanism. We derive a way to rewrite calls to the foreign functions into calls to the functional model. If you have proofs of the VST specifications that we generated earlier, then using these rewrite principles becomes fair game. So here we use our rewrite tactic. Notice how our goal is now entirely about the functional model. And from there, it's straightforward to finish this goal. So before I finish the talk, I'm going to show you an example with side effects. So I'm not going to talk too much about it, but this is a mutable array example. We define the operational side with a free monad, and we write an interpreter for that free monad in C, though we haven't verified this interpreter in VST. And similarly, we can also prove properties about client programs of mutable arrays using the rewrite principles. So quickly to repeat the main takeaways from the talk. One, we have carefully chosen a pair of languages that helps us avoid the combined language approach to multi-language semantics. And two, VeriFFI allows the user to reason conventionally in Kork and VST separately and connects these proofs together. And three, once again, since we're reasoning about Kork values within Kork, when we describe Kork values, the describer and describee are the same, which allows concise and type-safe annotations. So that's all I have time for today. For details about the specifications, our paper is the best source. For details about metaprogramming, my dissertation is the best source. More details about programs and mutations and side effects are also discussed in both. So there's some more feature work that we want to do. Most importantly, we want to complete the end-to-end compiler correctness proof of Kork for open programs and state how that connects to VST. We have an incomplete but mostly finished compiler correctness proof for Kork for closed programs, but that's now out of date. We discuss in the paper how this work can help us state the theorem for open programs. And the other feature work that we want to do is to finish the VST proofs for programs with side effects and mutations. So I want to leave you with this final slide of comparisons with similar projects that I have a hunch that most of the questions will be about. Thank you very much.
Let's see, we have quite a bit of time for questions. Okay, let me start. So the proofs, you mentioned that if you're trying to make a proof sort of in terms of the function, there is a rewrite into user. So is that rewrite part automatic, or is it the principle that the Kork user should be using to go about their proofs?
So we generate the equalities, which you can use to rewrite by hand. So you have to rewrite it by hand. Like if, like in this slide, we have the props and foreign rewrites tactics that do the rewriting for you. But the equalities are auto-generated.
Okay, cool.
I have a question about looking at the UN63. Is there a way to possibly abstract between different types of integers? Because it would be great if we were reasoning, for example, about 32-bit integers. Is there a way to do that within this framework? Or does that have to do with the VeriFFI types you were talking about earlier?
I guess you can put them in the same module. That sort of helps get around that problem. If you have multiple abstract types in the same module, could you do it cross modules? You could I think you can. I'm not sure. You have to try, but yeah.
I guess to my point, it'd be great to try to have similar proofs for example, if you're doing with 32-bit versus 64-bit. Try to have that be as general as possible, and then convert it to the number of bits you need. Does that make sense?
Yeah, I think it should be possible. I can try and get back to you.
I was wondering how usable is this setup if you want to make proof about a seek function without providing an equivalent Kork function, but just axiomatizing abstract property about it?
So you don't have to, so for the operation, so one, I guess I should differentiate two things. If you just want the operational side, you don't have to write the proof. You probably could also axiomatize the VST proof and just assume that it exists and do the rewrites and stuff. Should be possible.
The function then translates that to the corresponding VST property.
You can just do the functional model also as axioms, and you can just admit it, all the VST proofs, and yeah. That's what you're saying, right?
No. I mean, if I have my as a C function and I give it the Kork type, and then I write a property about that Kork type, and then translate it into a property about the VST function, and then prove that, and then get the property about the C.add without providing an fm.add.
I'm not sure I'm following. We can talk afterwards if you want.
Yeah. Okay.
Yeah.
Question on this side.
Hi, Max, University of Michigan. So I had a couple of questions. First of all, are you proving total correctness of the C programs? They're all terminating?
No, VST doesn't prove termination.
Okay, so they're all partial programs.
Yes.
Okay, so that addresses that. The other one was about this usage of HOAS, and where in your pipeline with the metaprogramming is that HOAS used? Is it used before the metaprograms are expanded?
No, it's used in our intermediate representation. So here. So
the programmer's not directly writing these?
No, these are all generated.
Okay.
This is just a technique that we developed that we think is interesting enough to present here. Normally you have to...
So the programmer's not writing the...
The programmers are not writing this, but...
Not writing it in HOAS is what I mean. Or they're just writing normal Kork types.
They're just invoking metaprograms, and those programs use this. But I guess they can use this when they're writing proofs.
Okay, thank you.
Yeah. Okay.